Hello all. Today we are going to start with the topic of trees, the non-linear data structure. Till now, we have already gone through the different data structures like arrays, stacks, queues, linked list. All data structures we have seen, we have implemented, and all of them have different or a peculiar manner of organizing the data and accessing it. But what was common among all of them were the data structures which were arranging the data in a sequential manner, in an ordered manner. Today we are going to get introduced to a data structure which is not a linear data structure. It is a non-linear data structure. So what is the difference between linear and non-linear data structure? In a linear data structure, the data is organized or arranged in a linear or a sequential manner, and it is ordered in such a way that with the base information, we can sequentially access all the elements present in that. But not every time we are going to encounter the data that way. We may be encountering a data which may not be stored in a sequential manner, may not be accessed in a sequential manner. That's why we are going for another type of data structure called as non-linear data structure. The array, stack, queue, linked list fall under the category of linear data structures, whereas trees and graphs are the data structure which are non-linear data structure, where the data is arranged in a hierarchical manner. In a label-wise access is provided. So we can organize the data in a hierarchy, and with the help of that, those hierarchical labels, we are going to access the data. Many a times what happens when we perform the operation on a linear data structure, as they are stored and accessed in a sequential manner, if the size of data grows, the complexity, the time complexity or the time consumed will increase with the size of data. But nowadays we need to access huge amount of data. We are provided with bulk of data. Continuously the data is getting generated. At that time, handling the data sequentially will not be an advisable thing. Rather than we'll opt for a hierarchical data and like a tree structure which will allow you a quicker or easier access to the data as it is a non-linear structure. What exactly falls under the non-linear data structure? We can say that it may be a hierarchical arrangement of the employees in an organization. Probably we need to design a plant or animal kingdom or vehicle kingdom, that if you want to present that kind of data, then yes, that is called as a hierarchical data and will be difficult for us to manage with the help of linear data structures like arrays or a linked list. That's why we are going for the data structure of tree. Let us see what kind of data we can observe here. Here, as I said in the example, animal kingdom. If I am representing an animal kingdom and I want to just represent it and access it. So animal are broadly categorized into two parts, reptile and mammal. Reptile are these are the categories which fall under a reptile category, and these are the animals which fall under mammal category. So this is main category animal, then subcategory reptile. In that also we have subcategories as snake, birds and lizards. In that also we have different categories. So the data is arranged in a hierarchical manner. If I'm saying that what is basal? Basal is a cow. What in general, it is a bovine category of animal, and it is basically a mammal. So this way we can organize the data. Or other example is evaluation of expression. How can we have already seen the evaluation of expression in postfix and prefix manner. So we have traversed the tree, traversed the expression also in postfix, prefix and infix manner. So that example that here based on the priority, the data will be arranged. The data will be arranged. So you can see here, this would have been the innermost bracket possible. This is the innermost bracket. That's why we are executing it at first. When we'll get the solution of this will be multiplied with these two are multiplied together, and then this solution is subtracted subtracting c from it. So this is an expression tree which is giving us how hierarchically we can process the expression based on the precedences of the operators which are appearing in that expression. Okay, so this is also a hierarchical kind of data, or the thing which we all have done in our younger days. In the school workbook, we have arranged our family tree. So these are parents have grandparents, then parents, uncle, aunt, their children, cousin, father, mother's children. So this is the family tree. This is also another hierarchical example of hierarchical data. So if these kind of data is appearing and we are asked to store them, at that moment we'll have to take help of a tree kind of data structure. How these trees can be constructed, what are the types of it, how they'll be helpful for us to store the data, that we are going to see in this lecture. Okay, so the tree as a data structure. Tree is a hierarchical data structure which stores the information in the form of hierarchy style. In a hierarchical level, in the labeled format, it is going to store the data. It is a non-linear data structure compared to arrays, linked list, stack and queues, which we have seen already. And it represents the nodes connected by edges. Whatever data we are storing, that data will be stored as nodes, and those nodes will be connected to each other with the help of edges, the lines. And it is one of the most powerful and dynamic data structure or advanced data structure which is particularly used for searching and sorting the elements. So this will be a structure of tree. If you can see, generally whatever tree we see, the tree is will have a root and then it will grow in a vertical manner. The tree data structure grows in a little reversed manner. A root will be upside and the tree is going to grow downside. How it is happening? See here, A is having the next level as B and C. So A leads to B and C, whereas B leads to D, E, F, C leads to G. So B has no connection with G or C. Okay, so this is a tree data structure where we are calling this particular node as a root node. Root node will be the node to which entire tree will be connected. The base node, as the tree is connected, or all the branches of tree are attached with the root. Similarly, we are going to have a root node from which rest of the tree is going to get generated. Okay, so these circular blocks you can see are called as nodes. These nodes hold the information which we want to store or hold the data which we want to store. And the lines you can see here are edges. These lines which you can see here are edges. These edges are connecting two nodes with each other. These edges are connecting two nodes with each other, but in a particular manner. What is that manner? We can see that this A is leading to two nodes B and C. So what I can say is this is A is a parent of B and C, or B and C are children of A. In that manner we are going to store the data. So A is the parent of B and C, B is the parent of D, E and F, E is the parent of H. Okay, so in this way we are representing the nodes. Then only it will represent the hierarchy. Okay, so B is the child of A, E is the child of B and grandchild of A. In this way we are referring to this. Fine. Now A has two children, B and C. B can be B can be a single node or can be a subtree. What do you mean by a subtree? Subtree will also behave like a tree. It will have its root, it will have its branches, it will have its children. But that whole subtree will be the child of some higher level node. So in this case, B is the child of A, but you can see this itself is a subtree. And this is another subtree. This is another subtree. Okay. So A is leading to two nodes, B and C, whereas B is the root of one subtree, C is the root of another subtree. Okay. So these are the terms which you need to take care of. So there is a root which will have branches, and those branches will be further having, those children will be having further branches, and they will be probably a subtree or a single node. Okay. Then every node is going to have a child except the last level node. Last node, it is not going to have a child. The last node which doesn't have a child is called as a leaf node. It's called as a leaf node. Okay. Just you can analyze this with a tree. Tree has a root, has a stem, has branches, and further you have leaves. But that leaf doesn't have further branches. Leaf is the end of that branch. So similarly, in this, C is the end of this branch, and H is the H, D and E, F are the end of the other branch. So the nodes which are at the last level, which don't have any children, is called as a leaf node. Okay. And in this case, like A has two children, B and C, so B and C are called as siblings. Nodes having same parent are called as siblings. Okay. So what are these terminologies that we will see one by one? I will introduce you with the terminologies, important terms which will be continuously using. Root. The node at the top of the tree is called as root, and there is only one root per tree. There can be only one root every tree. Okay, subtree can be there. Subtree's tree root will be there, but that will not be the root of whole tree. There will be only one root per tree and one path from the root node to any node. Every node will be accessible from the root node. That we need to take care, because in array also we have a base address. In linked list also we have a first node or start node marked. Similarly, here we will have a root node marked, and from that root node every node must be accessible. That is the important thing. So then only it will be a tree. If no node, if any of the node is not accessible, the tree is not correct. Okay. Second is parent. The node which have, except root node, which have at least one child or at least one edge leading from it to another node is called as a parent node. One node, one link on one edge leading from that node to any other node is called as a parent. And child, the node below a given node connected to its edge downwards is called as a child node. Means if it is connected to some node and is following in a lower hierarchical level, then it is a child node. Leaf node, as I already told, which doesn't have any child, is a leaf node, the last node in the hierarchy. Subtree. Subtree represent the descendants of a node. If a node has further children, then that node becomes a root of subtree, and that whole whole structure is the descendants of that particular node. That node won't be the root node of the main tree, but it's that will be a tree in itself. What do you mean by visiting a node? Visiting refers to checking a value of a node when control is on the node. As I said earlier, root must have a path to every node in the tree. Okay, because why we need that? Because particularly this tree is particularly used for searching purpose, and for that searching purpose we need every node or every value stored in the data structure must be accessible, and root is the only possibility to reach to every node in the tree. Okay, and there only the visiting happens. When we visit that tree, that node we mark it as visited, and then we will not again visit it if that is not the intended data to be searched. Okay, and traversing is when we pass through every node in a specific order. It is called as traversing. Traversing will be a separate topic to be discussed under tree that we will take later. But it is traversing means visiting every node in a particular manner. Then height of a tree, height of a node. Height of a node is the number of edges from the node to the deepest leaf. Means at that height it is available. Okay, at that height it is available. So to the deepest node. So whatever is last node, uh, if it is having two edges in between, then we'll say that it is having a height of 2. And levels of a node represent the generation of a node. If the root node is at level 0, we'll generally consider that root level as 0 level, then 1 level, 2 level, 3 level, and so on. Okay, path. What is a path? Path refers to the sequence of nodes followed from one node to another to reach from one node to another. Keys. Keys are the values which are stored in every node, and only those will be searched at the time of searching operation. The search key value. Height of a tree. Okay, what is the height of a tree? Height of a tree represents the height of its root node. Means from the root node till the last node. How many number of edges are there? That will be the height of tree. And depth of a node represents the number of edges from its root node to the particular node. What do you mean by degree of a node? Degree of a node represents the number of children of a node. Okay, number of children of a node. If I am just going back to the tree, the example tree, I'll just erase these things off. Now, what are the different terms which we have seen? The root node, this is the root node. Okay, you can find that every node from this root is accessible. We must be able to access every node. Okay, then what is a subtree? Subtree is the collection of descendant of that particular node. If I am talking about subtree of B, it is going to give you all the descendants of subtree B. Okay, subtree B. Then what we had is parent, child, leaf, subtree, visiting. So child, what do you mean by a child? B and C are children of A. G is a child of C. F is a child of B. So there are children. If there are children who have same parents, then they are called as siblings. So here B and C are siblings. D, E and F are siblings. Okay. So that way we can G doesn't have a sibling. Child and parent relation is this one. Traversing means I need to visit all these nodes one by one, not repeating any one of them, and visiting all the nodes in the tree is called as traversing of a node. Whereas if I am visiting that particular node, I'll mark it as visited so that in the current traversal, I am not going to visit that again. then only traverse is successful. Traversing means traversing all the nodes in a particular manner without visiting any node twice. Okay. What do you mean by height of a node? What do you mean by height of a node? Height of a node is the distance from the deepest node or the leaf node. So what is the height of A? Height of A is 1, 2, 3. It's 1, 2, 3. So height of A from the deepest node is 3. What is the height of C? Height of C? Height of C is only 1. Okay. What is the height of tree? From the root node till the last node. That is the height of tree. Okay. What is the level? Level root is at level 0. So B and C will be at level 1. D, E, F, G are at level 2. H is at level 3. So this way we can decide with the levels of a tree. Okay. What is the depth of D? How far it is from the root node? It is 2 edges away from the root node, hence depth of D is 2. Okay. So these are the terminologies which we have seen as far as tree is concerned. Tree is one of the very important data structures which is basically used for a searching purpose. Means what exactly happens here? How this node is represented? Node is not represented in this way. Node will be represented the way we are representing a linked list. It will be represented in this way, whereas the data will appear as one of the field of that structure. Then we are going to have a left child and we are going to have a right child. Okay. So then it will lead to two more nodes. It will lead to two more nodes and that will be stored in the same. If I am just replicating the existing one, so this will be its left child, this will be its right child, this will be a left child for C and this will be the right child for C. Okay, this way the tree will be constructed. If I am talking for this, there will be, so here there is not only left child, right child, but instead I can name it as child 1, child 2 and child 3 as D, E and F. So this way the data will be stored in a node of a tree and that search key value we are checking to get the value immediately. This saves time. How it saves time? Basically tree is a data structure which stores the data, but when we try to use it for searching, there is a particular modification which we need to do here as a binary search tree. This binary search tree will help you to store all the smaller value to the left of root and all the larger value to the right of root. So what we do while searching in that case, we just compare the value with root element, and if it is smaller, then we just search that value in the left subtree. If the value to be searched is greater, we just search it in the right subtree. What happens in because of that is the searching operation suddenly reduces to half, because as soon as you compare it with root and you find that the value is smaller, value to be searched is smaller than the root, the right subtree is immediately rejected. Okay, so that will, this way we can reject half the elements in with only one comparison, which was not possible in the sequential execution. That is why tree is supposed to be the stronger data structure when we talk about the uh, searching operation or data access operations. So in the further discussion of tree, we are going to see how a tree is managed in a binary form, that is binary tree, and how that binary tree can be further modified to become a binary search tree, and then how it can be implemented for further use. That will be our point of discussion in next time. I hope you have understood this. If not, please go through the lecture once again and try to understand it so that the next concept will be very clear to you. Thank you very much.